Welcome to the Data Centered Leadership Podcast. Today we have an exciting guest who is working on an incredibly important problem. His name is Adrian Gonzalez, and he's a professor at the University of Romulo Gallegos in Venezuela. He works on agricultural engineering and data science for milk production. So thank you so much for taking the time to interview Adrian.
Okay, thank you, Tyler, for having me here. I very appreciate this opportunity with you.
So let's get started. What excites you the most about applying data science in agriculture?
Well, in my research, what excites me more is the development of systems, of integrated sensing system that combines satellites, combine unmanned aerial vehicles, and ground systems, for instance, weather stations and things like that. I always try to use as a starting point for developing those systems the business perspective, the end user's view, because as you already know, my users are, my clients are farmers that they have a specific operational requirement regarding timing because of the crops, spatial details, and product quality. Other things that excite me most is, as I said, the flexibility that's unmanned drones. Let's say drones. Do you understand drones? Drones, unmanned aerial vehicles?
Yeah, unmanned aerial vehicles, UAVs, yeah. Are you using cameras, drones?
Exactly. So I think it's very exciting the way, the flexibility that these devices are providing for the development of these systems. In my research, I also like very much the use of multispectral data and hyperspectral data, process them in order to generate quantitative image product to generate some insight for farmers and commercial group, etc.
So when you say incorporating multispectral and hyperspectral data, are you saying that you're using some data from specialized satellites, or are you putting specialized sensor cameras on the drones instead of just using a regular visual spectra camera?
Okay. So some farmers have got their drones and they got their cameras, and when they got that, I can process this image. When you are dealing with farmers that don't have any vehicle of this kind, I work with satellites, let's say Landsat 7, Landsat 8, Sentinel-2, etc. Well, I use those kind of data. When I'm talking about Landsat, it's just multispectral. Hyperspectral is just when people have some those aerial vehicles, they got the special camera for those devices.
So is that like multispectral and hyperspectral? So is that incorporating infrared, UV? Which parts of the spectra are you interested in?
Yes. Well, for vegetation, infrared is very important, but we use also the visual part of the spectrum as well in order to achieve, because you never know when you are dealing with some insect attacks, some bacterial diseases or fungi diseases, you never know where the diagnosis signal of the class. When you are trying to classify, let's say, a fungi disease, you never know where is their signal that allows you to classify this class or to separate this class from the rest of the signal. So I always use as much as signal as I can But of course, when you do multispectral, you only are exploring several regions of the electromagnetic spectrum, the green, the red, the blue, the near infrared, far infrared, which are very important for vegetation, but sometimes there are some signals as more other regions of the electromagnetic spectrum that helps you a lot with certain kind of problems. That's why hyperspectral is very important, but not always is feasible, or because it's more expensive and it's not always available
Yes.
most of the people.
Interesting. Thank you for sharing. So you said that you focus on using drones and looking at the hyperspectral, all different parts of the spectra to gain data analysis. So you kind of elaborated. So would you say those are the types of problems that you're focusing on the most, like with related to agriculture and milk production? Would you say that the types of problems you find the most are things like trying to identify crop diseases and figure out ways to minimize their spread?
Okay. For instance, in people mix crop livestock systems, uh, sugarcane, maize, sorghum, you find a lot of problem with weeds. Uh, Weeds, when you detect weeds early, when the problem is small, is, let's say, easy to control. When the problem is big, you have to use
Oh,
herbicides
okay.
or chemical products, yeah, that are very expensive, are not always you can find in Venezuela. So when farmers realize that they got a weeds problem, it's too late. It's normally too late. Or when they realize they got an soil erosion problem, is too late to solve the problem, or too expensive.
Mm-hmm.
These technologies allow us to detect the problem when it's very small, when people is no worry about it. And so what we do is provide early warnings to the farmers, and show that this small problem is better too. And they are very happy with those situations. Not everybody see the benefit at the moment, but people who has spent a lot of money trying to solve a problem with weeds or erosion knows that early warnings are big things when comes some time.
Nice. Sounds like you're saving a lot of money and resources with your techniques.
Yes, and the approach that I use is, I use time series for, I organize the images. Basically, is the steps are detection, monitoring, and characterization of change.
Wow.
Basically, I center my work in that, in detect change. And for that, I use mostly models of time series. Also, I deal, as you saw in the book chapter, with supervised and unsupervised classification problems, and a lot of dimensionality reduction. For instance, in the side of the time series, I have to automate data processing. I have to automate the extraction of data from archives. Let's say for the websites in the case of Landsat, or for the cameras from when I download the image that the drones produce, calculate vegetation indexes, crop the data to match some desired spatial extents, some particular field.
Okay.
Apply some cleaning to the images, cloud and land masking, and also create some spatio-temporal objects, like, let's say, raster stack,
Raster stack?
Raster stack. The satellite and drone images comes in a model which is called, in a data model which is called raster. And you prepare some stack, 200, 300 images, 5 years, 3 years of history of a field, and you stack this information, and that allows you to construct a time series of this field or something like that.
Very interesting.
Yeah, and part of my job here, once I got the images and I automate all of this, well, I have to deal with functions that act as a batcher that includes some support for parallel computing, and create mosaics of tiles in order to improve the visualization of the images.
Wow.
To allow the farmer to see the pattern that I like to show them. I also have to deal with some functions to create raster stack. For instance, raster stack of a hyperspectral images are a little bit difficult to me that are starting on this. So I have to study that much more. But I have completely control of creating those stacks with multispectral images and other data. Then, well, once you got your images, you have to be able to generate an inventory, because when you extract your raster, you can combine several sensors, right?
Mm-hmm.
But when you are going to construct your time series, you have to do it just with what sensor, because there are differences between them, and you cannot always combine them for analysis. But the thing is, yeah, you got all the information in just one stack. And the data inventory part allows you to select sensors from those stacks of images. You know what I mean?
So you're saying you collect all the sensor data and you try to align it based on time and do masking, and you get it all in one group, so it's easy to play with for modeling. But then once you do the modeling, you don't put multiple sensors data into one model. You do separate models for every sensor, and then maybe like use the sum of the outputs from the models or something like that to determine if there's a problem with the farm or not.
Exactly, you're saying perfectly. Yes, because there are big difference between some sensors, spatial difference, radiometric difference, and you cannot always. Sometimes you can do, but not always you can mix several sensors. But it's nice to have everything in one stack, and that's make your life easier at the time of to retrieve data to do some analysis. Well, after this data inventory, because what happened with the data inventory, you can produce data frames with the name of the sensor, the time when the image was created, the path and route that the sensor follows. As I said, acquisition time, and produce a data frame that allows you to use this information and discriminate and do another thing for further analysis.
Wow.
Then you go to the validation. You have to make sure, as I said before, you have to do some cleaning. In this cleaning, you lose some data, because when you go, for instance, when you work with satellites and eliminate clouds and clouds chase in the image, you lose some information. But in the stack of raster, it's difficult to see where the information is and where the information is not. Because you got images for several times of the year. Sometimes there are clouds, sometimes there is not. These functions that help you validating your data observation drills through your raster stack and count pixels, and then tells you which part of your image or your farm has got very good quality data and which part are not. So there are several activities that you got here, and you have these activities pretty much are the same which each problem, but sometimes you have to do some adaptation depending on the problem you are dealing with. It's not the same when you are dealing with deforestation, or when the farmers like to be very precise determining biomass, because sometimes they want to know exactly how much biomass they got in the field in order to know how many cattle and for how long the cattle have to remain to stay in this field, and that's very important. Another thing that we do is to the quality of the biomass. We are exploring new ways to determine to quantify if the grass is losing quality, or if it's not, this is still good for cattle, etc. We are making big progress with that.
Wow.
Yes. Another thing that we once we got all our data inventory, and we have done some pixel-based testing, we are able to do the actual spatial analysis. In here, basically, what sometimes, well, you have to deal with big areas. There are farms. Recently, I worked in a farm. When I told you that I was in a field work, I was working in a farm in the south of Venezuela, which got 39,000 hectares. So
wow,
very big farm. So that's kind of farms are typical of the south of Venezuela and in the Cerrado, Brazil. Have you heard about that? Well, let's say these farms are typical of flooded tropical savannas.
okay.
But in the world are very important because in there you can produce a lot of meat and a lot of milk for people. No? If you use the right breed of cattle, you probably have a good business with this savanna. Well, in my analysis, what I do is, as I said, I use some models. I calibrate some models. I have to be very careful with parameters because not all time series are the same. It's not the same a time series for a forest that for a grass, etc. My objective here is to detect breaking points. Breaking points are changes that are different. For instance, if you are evaluating 10 years of images in a field, you have to, when I detect a breakpoint, this means that it's a change that is different to the normal stationary changes of this vegetation. Now the vegetation that is within the field, the field. Do you understand me? So
when you say breakpoint, are you saying like if data is missing, or are you saying if there's that the time series model detects some key change in the data?
Yes, a change. It's a particular type of change, which is different. You know, vegetation during the year, the vegetation change normally.
Oh, I see.
During the rain season, there is a lot of photosynthetic activity, and during the dry season, this goes down. But there is a trend during years that you cannot tell with it's not easy to tell when you don't know models. So breakpoint is a change that is not equal to the normal stationary changes
Ah,
vegetation. No? My system is can produce an early warning of those changes. I can say where and when those breakpoints are occurring. The way that I show that to farmers is I produce several raster products um, uh, per year, put by month of the year, where are located, where start the breaking points in a particular year. And we go to the area where the breakpoint is occurring and show him or show them what is going on, and talk about this kind of thing. That's what the system does. Another thing is that not only the breakpoint, but also we are able to see the magnitude of the change. For instance, if you are dealing with the vegetation index that talk about photosynthetic capacity, I can tell you where, in what part of your farm or your grasses are you losing systematically photosynthetic capacity during the last 2 years or 3 years or whatever. Okay,
mm-hmm.
so basically, in my monitoring, you detect special changes that are those breakpoints and the magnitude of those changes. That's basically what I do.
Wow. It sounds like your system is quite complex. Like you start with multiple data sources, then you do time series and also, well, you start with multiple data sources, then try to find differences, which sensors are seeing the most changes, right? Then you do a time series on each set of sensors to help you detect the breakpoints. But then once you have the breakpoints, you also need to do some different modeling and visualization to localize to find the localized regions of the changes within the data sets.
Yes, and sometimes it's very, you need some computing power because you have to do that in each pixel of image. In Landsat 7, for instance, a pixel is 30, a pixel has 900 square meters.
Mm-hmm.
Well, you can imagine how many pixels are in a farm with 39,000 hectares. So you need sometimes computer power to do that because it's very dense from data point of view. Fortunately,
fortunately, yeah.
Unfortunately, there is cloud computing now, and you can do some resources. You can use those resources in order to alleviate this situation. But yes, that's basically what we do with the information. And also the multispectral and hyperspectral information, you have to combine that with some, let's say, temperature data. You have to create some thermal calendars because plants and insects, when you got problem with insects, they move according to a thermal calendar. No, the normal calendar that people used to work with. So when you use thermal calendar, emerge some patterns that you are not able to see otherwise. So combining ground in situ systems or ground-based systems with unmanned aerial vehicles and satellites, it's possible to do a monitoring that is
Wow.
very, very reliable.
Amazing.
This is the word. Yeah.
Wow. Thanks for sharing. It's definitely the level of detail in which you're explaining this and the level of complexity. It's eye-opening for the helping me to understand what it takes to develop a useful, robust set of models that work over time for solving these problems.
Yes. The ideal in the ideal world, it would be that I can create an application that take into production, all those code that I got in a kind of dispersion in my computer. I have to put in one application that and put into production. But this is the next level. This is maybe next year level when I acquire all the knowledge to do that. But I'm on my way now to doing that.
Nice. That would be something like what, like moving from pandas to like a Apache Spark, like automated data pipeline, and going from like somebody manually piloting the drones to get the footage versus having the drones on an automated set schedule of piloting to do the raster video, right? Because the satellite data already comes at a regular interval.
Yes.
And the other sensors come at a regular interval, but the drone data is more susceptible to some time changes.
Yes.
So you get the right drone data, and then you, instead of using like a single computer solution, you use like the streaming solutions. Is that Apache Spark? Is that what you're looking into?
Yes, that's my dream.
Nice.
Yes, that's my dream. But you have to do well. There is already people in the world that do that. There are many applications that do that in the world. But let's see if this approach. But that's the way that, as you just said now. That's the way as I'm planning that things are going to be in the near future. Yeah.
So is that what you would envision as the future of agriculture and data science? Is that the big picture, the long-term vision, to have like dashboards for the farmers?
Well, I like very much the name of this meeting, the name that you choose for this meeting, because that's what move some people. I try to think in the farm of the future. The farm of the future have to be self-sufficient in the sense of the water supply. You have, I mean, farms need to provide themselves with the water. They have to provide themselves with electricity, and probably they are going to have to, or they must provide themselves with biofuels or something like that.
Wow.
And be independent, self-sufficient in that kind of things. But on the other hand, they have to be very connected with agribusiness chains, right? With the end consumer. So that's a challenge for farmers. Farmers of the future have to be not tolerant with erosion. This is a big problem now in agriculture. In order to do that, you have to make, this is as you probably are imagining now, this is a multidisciplinary task. So you need a lot of data for hydrology, atmospheric, the weather data. You have to deal with all of that in an applicable way. You have to have application that allows you to use that easily. yes, I'm convinced that this is the future of farming. Farmers in the future are going to be using more APAs for weather data. They are going to use more cloud computing. So
Wow.
they now are reluctant to use this technology. Well, at least in Venezuela, they are reluctant, but I think this is going to change. This is, the farming is going to evolve to a situation where they are going to use this kind of technology with more intensity, let's say.
Amazing. So beyond yeah, so I guess it sounds like you're saying the next step is the dashboard, but then after that maybe you will go so far as to have automatic triggers like cell phone notifications or even direct links to the farming equipment. And if like every piece of farming equipment is like a drone, automatically controlled, automatically piloted, you can use this brain to trigger and tell the equipment when to do the harvest or weed mitigation or anything like that. And then one farmer can manage a much larger plot of land. And then the next step is focusing on forecasting or trying to predict which types of crops people are more interested in eating to decide what to grow when.
Yes. Well, it's funny because what you have just said, I was 2 years ago, I was working with a company. Um, we were trying to develop for the sugarcane industry in Venezuela applications like this.
Wow.
We were there was some prototypes of applications that from mobile phones you can see your farm, and we were able to produce some early warnings for some with some vegetation indexes. But the the the, the objective here is that the farmers could have could, could perform the monitoring of the farm. You know, in here in Venezuela, sugarcane growers sell the product to a sugar center or something
Okay.
like that. And that sugar center serve as a pivot who control, you know, hundreds of farms,
Wow.
and they want or another level of control. They want to be informed of what is happening in each farm, when is the harvest going to be in that part of the territory, when you have to concentrate your resources in this other part. In sugarcane, weeds are very problematic because
Hmm.
when you go to the car, when you go by car, uh, seeing the fields, you only see the outside part of the field. You don't see the center. So you never, when you realize that you got a problem with weeds or some fungi or something like that, is normally too late.
Wow.
You have to invest a lot of money to solving the problem. When you use this kind of technology, when you use infrared, for instance, infrared tells you when something is happening with healthy plants. Um, if you use hyperspectral images, you have information for many parts of the infrared sector. So it is possible to get realistic warnings using this kind of data. So yes, that's the thinking that we are dealing all this time. But you know, a crisis, sugar price of sugar in Venezuela is ridiculous. Is controlled by the government. So you cannot do any planification. So farmers now are surviving. They are not investing now in drones or satellites. They are not investing in that. They are just trying to save their farms, or they are leaving the country because, you know,
Wow.
the situation here is very difficult at the moment. But we think this is going to pass, and we are getting ready for the future, for the democratic new democratic government in Venezuela, hopefully.
Great. Wow. Yeah, thank you for sharing, Adrian. Thanks again for speaking with me. This is it's been enlightening, really interesting work you're doing. It sounds like something that is definitely going to help the world, help us become more efficient, help feed people. I mean, it's really important on many levels. So thanks for your contributions to society.
Thanks to you as well. I promise that, well, my English must be better next year or shortly. And my ideas about this is going to be more organized next time. Well, I enjoy the conversation, and I enjoy meeting you.
Have a great day.
Okay.
Bye.
Bye. Thank you.